Hello. In this video, we're going to look at some basic curve sketching techniques. Now, the motivation for this section would be the idea of sketching a curve. And if you had to sketch a graph like this, well, you know some techniques from pre-cal. In particular, this is going to be a parabola because it's squared, and the vertex is going to be at 3 and -4. So that's enough information, I think, to actually sketch the graph here. We could throw down an xy axis, go over to 3 and then go down to -4. Throw ourselves a little vertex there, and we'd get a parabola. And that curve is not particularly difficult to sketch, but how do you sketch something like this? Well, clearly it's not a parabola because it's got degree 4. And maybe there is some factoring you could do from pre-cal. Sometimes we know we can find the x-intercepts and factor it, but sometimes these things won't factor. And even if it does factor, it might not tell you everything about the graph in terms of the minimums and maximums, the hills and valleys. So we need some new methods, some new techniques for sketching more complicated graphs. And in particular, what we're going to use is calculus. We're going to use the idea of the derivative to help us sketch the graph. Now, we have some theorems here that we alluded to in the previous problem-solving question. In particular, if we have a function, of course it's got to be continuous and differentiable. If the derivative is positive, then it means the function is increasing. Now that might almost be obvious for you. You might not think that needs a proof, but it does need a proof. We need to show that that's what the derivative tells us. But it should make sense. If the derivative is positive, it means the slope is positive, so the graph should be going up. If the derivative is negative, then the slope is negative and the graph is decreasing. And of course, if the derivative is 0, then the graph is constant. So let's look at the proof of the first one. So proof, we'll do number 1. Now, just like a previous proof, we need to use the subinterval method because we are looking right here, I should point out, on the interval a to b. We're going to want to use the mean value theorem to get this proof underway, and to use the mean value theorem we need continuous on that closed interval, so we have to use the subinterval technique. So we're going to let x1, x2 be a subinterval of a to b. And now we are going to apply the mean value theorem on the subinterval x1 to x2. Well, the mean value theorem says that f prime of c equals f of x2 minus f of x1 over x2 minus x1, where c is in the interval of x1 to x2. So c is in that interval. Now here's the thing we know. Because we're doing part 1, we're going to assume that the derivative is always positive. Well, if the derivative is always positive, then the derivative at c is also positive. So we could say, but f prime of c is positive. Now, what do we know about the bottom here? x2 minus x1. Is that quantity positive or negative? Well, we have a subinterval. We go from x1 to x2. This is the left side of the interval. This is the right side. So this is the bigger number. This is the smaller number. When you subtract two numbers like that, of course, you get a positive quantity. So we could say, and x2 minus x1 is positive. So let's think about this top of the fraction. If the left-hand side is positive, so overall the fraction should be positive, and the bottom of the fraction is positive, what has to happen to the numerator? Could the numerator be negative? Well, a negative divided by a positive would be a negative, and it's supposed to give us a positive in the end. Which means that the only option we have is the numerator must be positive. So it's a positive divided by a positive to give a positive. So we would say, thus, f of x2 minus f of x1 must be positive. Well, we could move f of x1 to the other side. So, thus, f of x2 is greater than f of x1. Well, what does that mean? If f of x2 is greater than f of x1, this is the definition of increasing. So we would say, hence, fx is increasing on x1 to x2. And f of x is increasing on a to b. Because if it's increasing on x1 and x2, and x1, x2 is any subinterval, then clearly it's increasing on the whole interval. So let's do the same proof now for part 2, where f prime is less than 0. So part 2 here, again we let x1, x2 be a subinterval of a to b. We apply the mean value theorem on x1 to x2. So we get that f prime of c is equal to fx2 minus f of x1 over x2 minus x1, where c is an element of x1, x2. But of course, f prime of c now is less than 0. And x2 minus x1 is still a positive quantity. So this side is negative, and this is positive. So the overall fraction is supposed to give us a negative value. What has to happen to the numerator? Well, if the top is positive and the bottom is positive, it gives us a positive fraction, and that's no good, which means the top has to be negative. So, thus, f of x2 minus f of x1 must be negative. Thus, we could move it over to the other side, and f of x2 is less than f of x1. Well, this means the function is decreasing. Hence, f of x is decreasing on x1 to x2, and f of x is decreasing on a to b. Now for part 3, we actually prove this in the notes, so this is already done, already proved. See your notes. And that's the proof for all 3 statements. So as a remark, by the above theorem, if fx is a differentiable function, to find the intervals where fx is increasing or decreasing, all we have to do is write the sign diagram of f prime x. Now this leads us to a really nice theorem, which is called the first derivative test. So there's a few parts, and we'll look at the first part here. Let's let fx be a function and c be a critical number for fx. If there exists an open interval ab containing c, such that fx is continuous on ab and f prime of x is greater than 0 for all x in the interval a to c, and f prime x is less than 0 for all x in the interval c to b, then fx has a relative max at x equals c. Now I know that's a lot of words, but let's go ahead and draw a quick diagram to see what's going on here. So we have an interval a to b. And in that interval, we have some number c. Now, what we have is on the left side, from a to c, we're told that from a to c, f prime x is greater than 0. So that means the derivative is positive over here. We have f prime of x being greater than 0. Now on the other side of the interval, from c to b on the right-hand side, we know the derivative is less than 0. So here, f prime of x is less than 0. Really, here it's positive, and here it's negative. So imagine you have a graph that's increasing and then decreasing. Well, what's happening at the very top there? Of course, you have a relative maximum. And so that's the picture and that's the diagram. It almost feels like it's proved already, but we need to write it down in words so we have an actual proof. So here's the proof. Since f prime of x is greater than 0 for all x in the interval a to c, by the previous theorem, f of x is increasing on a to c. Now, what that means from a picture, of course, is that the function is going up, going up, going up, going up, going up on the interval a to c. Well, if a function is increasing on the interval a to c, then the point f of c is going to be the highest point all the way along because you've increased and then you've increased some more and increased some more. So we could say that f of c is going to be greater than or equal to all of the other values here, f of x. So we could say, therefore, f of x is less than or equal to f of c, or f of c is greater than or equal to f of x for all x in the interval a to c. We're going to call this point number 1. This is our first piece of information. Now let's look at the other portion of the interval. Since f prime of x is less than 0 for all x in the interval c to b, by the previous theorem, f of x is, well, in this case, decreasing on c to b. And that's what we drew over in the diagram here. The function is decreasing on c to b. Well, again, if you think about it, if a function is decreasing, then the highest portion on that interval is going to be at the beginning, because you start out at a top and you decrease, 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 decrease. So, we could say then, therefore, f of x will be less than or equal to f of c for all x in the interval from c to b. We're going to call this point number 2. Now, clearly, if you think about it, f of c, well, it's equal to f of c. So we could say f of c is less than or equal to f of c. Now we're going to call this point number 3. Now I know that f of c is equal to f of c, but I'm going to say less than or equal to because the word less than or equal to, it means that it is equal to, so this is a valid statement. It's like saying 3 is less than or equal to 3. It's true. It's equal to, so it's less than or equal to. And I'm going to use this because if you notice, I have 3 points, 1, 2, and 3. Here I have f of x being less than or equal to f of c. Here I have f of x being less than or equal to f of c. And here I have f of c being less than or equal to f of c. And if you notice the 3 intervals, I go from a to c, then I go from c to b, and then I actually look at that point c. So I've covered all the points a to c, all the points c to b, and the point c, which means I've covered every point from every point from a to b. And at every point from a to b, f of x is less than or equal to f of c. So we can say, from 1, 2, and 3, f of x is less than or equal to f of c for all x in the interval a to b. Well, what does it mean for f of x to be less than or equal to f of c for all x in the interval a to b? This, of course, is the definition of the relative maximum. So therefore, f of x has a relative maximum at x equal to c. And there's our proof. Now for part 2, you can do this proof for homework. It's very similar to the first one. Let fx be a function and c be a critical number if there exists an interval ab containing c such that fx is continuous on ab, f prime x is less than 0 for all x in the interval a to c, f prime x is greater than 0 for all x in the interval c to b, then fx has a relative minimum at x equals to c. And so again, the diagram here for you, we're going from a, this is our one section over interval, to b. And somewhere in the interval we've got some point c. Over here we have a negative derivative. And over here we have a positive derivative. So the graph is decreasing and then increasing, which means clearly right there we must have a relative minimum. Now let's look at part 3. Let fx be a function and c be a critical number of fx if there exists an interval ab containing c such that fx is continuous on ab and f prime x is greater than 0 for all x in the interval ac union cb, or less than 0 for the same interval, then fx has neither a relative max or relative min. So we're not going to prove this one, but here's the idea. Again, we have the interval from a to b, and you've got some point c in the middle. Well, if the function is positive here, or the derivative I should say, is positive here and positive here, what you have is a graph that is, well, increasing and then increasing some more. And this point here is not a rel min or a rel max. It's really nothing important, at least for what we're looking at right now. And so if it increases and then increases again, or decreases and then decreases again, it's neither a min or max. You've got to have increasing, decreasing, or decreasing, increasing to get some type of minimum or maximum. So let's try some examples here, and I want to just make up a sign diagram example for us to understand how this would work. So let's say this was the sign diagram. I don't know what the function was, but we're just going to make up a sign diagram here for f prime x. Maybe you've got a 0 at -3, at 1, and at, let's say, 5. And let's say this is an even power. So we'll pick a number to the right. I'm just making this up. Let's say it's positive. So positive, positive, negative, positive. So what that means is the function is increasing, then decreasing, then increasing, then increasing. So if we look at the diagram, clearly this is going to be a rel max at x equals to -3 because it increases and then decreases. Over here, this is going to be a rel min because it decreases and increases. But this over here, this is neither. Nothing happens at 5 because it increases and then increases again. So I encourage you to make up your own example here for an example sign diagram. Come up with some type of sign diagram, put some zeros on it, maybe make a couple of them even or odd, and draw the signs and then see if you can identify where the relative maximum is or where the relative minimum is. Alright, let's do an example with an actual function. So let's let fx be x cubed minus 6x squared plus 9x minus 3. We're going to find the intervals where fx is increasing, decreasing, find all relative max and min, and then we're actually going to use this information to sketch the graph. So first up, let's find the derivative. 3x squared minus 12x plus 9. Looks like we could factor a 3 out of there. So 3 will come out as x squared minus 4x plus 3. And then we can factor as x minus 1, x minus 3. So we draw a little sign diagram over here. We've got a 0 at 1 and at 3. Pick a number bigger than 3, say 10, positive, so it'll be positive, negative, positive. So the graph is increasing, decreasing, increasing. So let's label those intervals. So where do we have increasing? So increasing. It's increasing on, well, negative infinity to 1, union 3 to infinity. Again, we use round brackets because it's not technically increasing at that point. It's a maximum or minimum. It stopped increasing or decreasing. And it is decreasing. Well, it's decreasing from 1 to 3. Now it looks like from the diagram that this point right here is going to be our relative maximum, and this point here is going to be our relative minimum. So let's try to calculate the y values associated so we can plot it on the graph. So we're going to find here f of 1. So this means, and this is important, we have to go back to the original function. If you were to take 1 and plug it into the derivative, just for fun here, you would get, well, 3 times 1 squared is 3 minus 12 plus 9, so it'll be negative 9 plus 9, you'll get 0. And of course you're going to get 0 because the number 1 is a 0 of the derivative. That's how we came up with the number 1. So please don't plug the number 1 into the derivative. It would be a classic mistake. Instead, we have to plug the number 1 into the original function. So let's see what we get when we plug it into the original function. We'll get 1 minus 6 plus 9 minus 3. So we work that out and we get 1. So that's going to be our relative max. Next we do f of 3. So we get 27 minus 6 times 9, so 54, plus 9 times 3, so 27, and then minus 3. So the 27's cancel with the 54, giving us negative 3. This is our relative min. Well, let's go ahead and sketch the graph. So this is our x-axis. This is fx. We know over at 1 and 1, we're going to have a point. This is going to be a relative max at 1 and 1. And then over at, well, 3 and negative 3, we're going to have a relative minimum. So we start over here somewhere. It's not maybe clear where the y-intercept is, but we could find that. We'll find f of 0 to grab that y-intercept. F of 0 is going to be, well, just negative 3. That's convenient. So there's our y-intercept. Start down here, and we know the function should be increasing. So we should start down here, and it should increase, then it should decrease, and then it should increase again. So we make sure to draw it smooth because it's a polynomial. And so we increase, and then decrease, and then increase. Now that might not be the nicest polynomial you've ever drawn. I can try doing a little bit better. Increasing, decreasing, increasing. Something like that. And as long as you get that relative maximum there, and that relative minimum, you're good to go. We can see the nice shape of the polynomial. Now, for this question, we haven't actually calculated the roots here, and on other questions, we may or may not find the x-intercepts. They may be important or they might not be important, but for the overall shape of the graph, what we're focusing on now, unlike in pre-cal, we really focused on those roots. For right now, we're focused on these hills and these valleys, these relative minimums and relative maximums. So let's do another example here. Let's let fx equal x to the 2 over 3 times x squared minus 4. We're going to find the intervals where fx is increasing, decreasing, and the relative max and min, and then sketch the graph. So the first thing we want to do, of course, is to find the derivative. We're going to need to use the product rule. So 2/3 x to the negative 1/3, x squared minus 4, plus x to the 2/3, and then 2x. Now we want to convert that because eventually we need to make this all common denominator and whatnot. So this would be x to the 1/3 on the bottom, x squared minus 4. And over here we have, well, I guess 2x times x to the 2/3. So this is missing, oh, don't lose that 3 on the bottom. So this is missing a 3x to the 1/3. And so we need a 3x to the 1/3 on the top over here. So we'll have 2x squared minus 4 over 3x to the 1/3. We can go ahead and clean up the top. 2 times 3 will be 6. And x to the 2/3 times x to the 1/3 will be x to the 3/3, so just an x. So 2x squared minus 8 plus 6x squared over 3x to the 1/3. Keep going with this. So we'll have 8x squared minus 8 over 3x to the 1/3. We could factor out an 8. So x squared minus 1 over 3x to the 1/3. And then we can factor that as a difference of squares. So 8x minus 1, x plus 1 over 3x to the 1/3. So now we have to take that and do a sign diagram. So we draw a sign diagram. We've got a point at 1 and at -1, and it's undefined at 0. So we pick a number bigger than 1, let's say 10. It's going to be positive, so positive, negative, positive, negative. So we know the graph is decreasing, increasing, decreasing, increasing. So right away we've got all sorts of interesting points. This is going to be a rel min. This is also going to be a rel min. And this point over here is a rel max. Now it's important to note that we drew this as an open circle because the derivative is undefined there. At these points the derivative is 0, which means when we draw it, it's going to have a horizontal tangent line. It's going to be flat. But here the derivative is undefined, which means we're going to want a sharp point. And so we're going to just label that here. This is a sharp point because the derivative is undefined, represented by that open circle. Now let's find the y values for these. So let's find f of -1, f of 0, and f of 1. So we go back to the original function. So f of -1, that's a little nasty. -1 to the 2/3, and then -1 squared will be 1, so 1 minus 4. Well, -1 to the 2/3, you'll square it to give you 1, and then cube root of 1 is just 1, so this will work out to -3. Now f of 0 is just going to be 0 to the 2/3, and then 0 minus 4, 0 times anything, of course, is 0. And then f of 1 is going to be equal to 1 to the 2/3, and then 1 squared minus 4, which will give us, again, -3. So let's go ahead and write down all the information we have. We know it's increasing, decreasing, increasing, decreasing. We should label those intervals. So maybe I'll put that right here next to the graph. So increasing, oh, maybe a little bit further away, give myself some space. Increasing. Well, it's increasing on -1 to 0, union 1 to infinity. And it's decreasing from -infinity to -1, union 0 to 1. All right, let's go ahead and draw that graph. So we'll label it as x and fx. We've got a point at 0, 0. We've got a point at 1 and negative 1. So 1 and negative 3. This is 1, this is negative 3. Then we've got a point over at negative 1 and negative 3. And if we wanted, we could actually find the x-intercepts. If we look back at the original equation here, this, if we set it equal to 0, we would get, well, x squared minus 4 would factor as x minus 2, x plus 2. And we have x to the 2/3. So you get x equals 0, x equals 2, x equal to negative 2. So we could add those intercepts if we want, just to help round out our graph, give it a little bit more detail. So we've got an intercept over here at negative 2 and 2. All right, so let's draw the graph. So we know it's supposed to be decreasing initially. Then we've got a rel min down here. Maybe we'll label that rel min. Got another rel min over here. And this point right here is going to be a rel max. So the graph should decrease, then increase, then decrease, then increase. These should be smooth down here with horizontal tangents. This one should be a sharp point. So let's draw that graph. So decreasing, rounded out, sharp point, rounded out. Away we go. So again, for the rest of it, it should be smooth because it's differentiable. But at 0, it's not differentiable, so it should be sharp. Now I'll show you the graph on Desmos just to confirm that this is what it looks like. So here we have the graph. We can see those wonderful minimums and maximums, and we can see very clearly here at the top, the function is not differentiable. Now, if you actually do a vertical reflection just for fun on this graph, you get something that looks like this. And it almost makes me wonder, is this the original graph for the McDonald's logo? Maybe this is where the golden arches actually come from. Interesting to see things like this when you start graphing functions. Now I'll do a few plicker questions here. First off, given f prime as this function, x minus 3, x minus 4, x plus 2, determine where fx is decreasing. So pause the video and give it a try yourself. Alright, so we draw a sign diagram. We've got 3, 4, and negative 2. So positive, negative, positive, negative. So where is the function decreasing? Well, here and here, which corresponds to D. The graph of f prime x is given below. Where is fx increasing? That's a bit of a strange question. This graph is f prime x. Where is f of x increasing? So think about it for a bit. Alright, so the answer is not going to be A. A is where this graph is increasing. But we're asked to find where the function is increasing. Well, the function would be increasing wherever this graph is positive, because this is a graph of the derivative. So notice it's positive in this region here, and it's positive in this region here. So it's actually going to be B. B is the correct answer because that's where the derivative is positive, which means that's where the underlying graph, fx, which is not graphed here, would be increasing. So we'll try one more example here. Fx equals to 12x minus x cubed has a local maximum at one of these options, or maybe fx does not have a local maximum. So give it a try. Alright, to find the maximum, we need to find the derivative, which is going to be 12 minus 3x squared. We can factor out a 3, and we're going to get 4 minus x squared, which we can factor as a difference of squares. So 2 minus x and 2 plus x. So when we go to draw that sign diagram, we've got 2 and negative 2. Pick a number bigger than 2, say 10, it's going to be negative, so negative, positive, negative. decreasing, increasing, decreasing. So clearly, we get ourselves a local maximum at x equals to 2, and the answer is B. So for homework, go ahead and sketch these two graphs, and then check your answer on Desmos. You can find the relative max and min, the intervals where it's increasing, decreasing, and then make sure you have a nice sketch. In the next video, we'll look at some more topics on curve sketching. Until then, thanks for watching.